Hello everyone. In this tutorial I am going to share with you some property of a linear vector space, right? So here I am going to discuss with you some properties of a linear vector space. So a linear vector space, it is denoted by V, is a collection of objects. So object 1, object 2, dot dot dot. So what is a linear vector space? So a linear vector space is a collection of objects. Now what are the objects? So the objects are nothing but the vectors. So we can say that a linear vector space is nothing but a set of vectors. Okay, as like we study the set, we said that a set is a collection of objects. So a linear vector space, which is head by V. And okay, so so far we have understood is that a linear vector space is a collection of objects, and the objects are nothing but the vectors. Okay, so actually here is an important thing. It is that we actually write in mathematics, we write a, so actually in mathematical physics we write a vector, let's say a vector as is, right? We write it by an arrow. But in quantum mechanics we denote a vector by this symbol. Okay, so it is actually called as the Dirac notation. It is actually called as the Dirac notation. Okay, it was actually physicist called Dirac who has actually given this notation. So here are some property of a linear vector space. So the first property, excuse me, let me just remove it. Okay, so the first property of a linear vector space is here actually, is that the result of the operation is another element of the space, which are called the closure property. We have two vector space. In this case the vector space is V and W. So these are the two vector space, and what I have said earlier, that a vector space is nothing but a collection of vectors, right? So if we have two vector space V and W, and if we add to vector space, the result, the vector space that we get after addition of V and W to another universal set of vector space. So for example, if I give you an example, is that if we let's say add an integer, so the addition of two integer will again an integer, right? So in this case the addition of two vector space will again give you a okay. So the second property of linear vector space is that the scalar the linear vector space follows the distributive property, right? And what is a distributive property? Let's say we have a vector V and W, and if we multiply with some, let's say, scalar A, then it follows this rule, A V plus A W. So it is the scalar multiplication of the addition of two vector space by a scalar. So what we have seen is that the linear vector space follows distributive property, and also they follow, it is called the closure property. What is closure property? If we add to linear vector space, then the answer will also belong to a linear vector space, right? Also here you see that the scalar multiplication is distributed in the scalar. So if we have two scalar a and b, and if we multiply the sum of a and b with linear vector space v, then it shall follow, as we know, the simple law of multiplication, ab plus av plus ev. Okay, here's the another property is that the scalar multiplication is associative. So yes, so what is this? The scalar multiplication is associative. Okay, so if we have so if we have a vector space v, and if I multiply the vector space by a scalar b, then again I multiply the whole. I multiply the whole by another scalar a, right? Another scalar a. So the answer will be av times a vector. And here is another property of vector addition, that if we have two vector space v and w, then they follow the commutative property. And what is commutative property? Commutative property is nothing but a plus b equal to b plus. Here v and w are those vector space, and if I add the two vector space in v plus w, and if I again add w plus beta, answer will be same, right? And here is another property, which is the addition is associative, right? So the addition of linear vector space follow the associative property. Now as I think all of you know that what is associative property. So if I have a vector space v plus within